I'm going to start looking at this kit. So this is a traffic light simulator kit. So this is from icystation.com, and this was very kindly provided to me free of charge by icystation.com. Perhaps we'll just look at the listing online. This is the circuit on the icystation website. So NE555 traffic light circuit kit, blah blah, price $4.39, so it's quite an inexpensive kit. And we have a parts listing here. So we have the 555 chips, so the timer oscillator chips U1 to U3, and the CD4011, which I think is a quad NAND gate if I remember correctly. So there's the active circuit components, some transistors, a whole bunch of resistors, some diodes, some coloured LEDs, and there's the assembled board. But unfortunately, no circuit diagram, no schematic. So it's quite difficult to figure out from this how it works. They do have a shot of the board here. So you can see the silk screen and so on, but no schematic. So we're going to have to work out that as we go along. So if we get this get the circuit board out of the bag, so the top of the circuit board is quite well labelled, so the silk screen shows very clearly where to put all of the components. So we've got the three 555s, U1, U2 and U3, and U4 was the CMOS chip, and various support components, these five transistors on the board also. The actual layout is a bit of a mess. I don't know if you can see this, but we've got all these tiny tracks, many of which route right around the board, going all these funny routes going through gaps. So sometimes what you get, I mean, it's a single-sided board obviously, but sometimes what you get is when there are a lot of tracks that have to go in the same direction, you can have wire links that go across the top of the board, which make the track layouts a little bit simpler, but not in this case. So it's quite difficult to actually figure out where anything's going on this board to reverse engineer it, and there's no circuit diagram available for this kit. So I thought what I might do is build it little by little, stage by stage, and document as I go, and end up creating the circuit diagram, because I don't really understand how this works. I don't know why it needs three 555s, because you only need one to be the clock provider. So I guess in some way these other 555s are being used as logic gates to give different patterns of the lights, but we'll find out. Now I think U2 is probably the astable oscillator that's providing the clock for the whole system. So I think what I might do is start there, and I'll just put in the components that support U2, and we could put the logic probe on there, or the scope, and make sure that's working, and then we could build from there and try and construct an idea of how this board is working, and draw the circuit diagram at the same time. So it might take me a few days to to do all the different stages stage by stage, but obviously I'll edit the video and make it all into one story for you there at home. Okay, let's get started. I've been looking at the circuit board, trying to follow the traces and work out the shape of the circuit diagram here. I've made some progress. It's very difficult following these tracks on the board, but yeah, I've managed to ascertain that U2 is the main oscillator for the system. So these are the components that I'm going to put on the board now, and that's driving a couple of things. So we have a diode and this link going to the CMOS chip, and it's also driving the transistor Q4 here, so I think I'll put that in the circuit as well. And this this output from the transistor is one of the traces that snakes its way across the board and ends up with the LEDs. So the transistors are obviously the LED drivers. So let me put these components on the board, maybe also Q3 as well, because I think that's the reset pin. So I think this is some way of stopping the oscillator. So I'll put some components in the board, and then we can start testing it and see how this part functions. Okay, so I've got the components around U2 now. So this is our astable circuit. Now looking at the combination of the resistor and the capacitor gives us the time constant. So that's 22 microfarads and 1 megohm. So that gives us a time constant of about 20 seconds. So this is running with a period of 20 seconds. And if we get the logic probe on here, we can actually see that in operation. So pin 3 is the output. Let me try and get this all in shot. So there, the 555 output is low, so we've got a green on the logic probe. But if I just pulse this pin, so this is Q3, the transistor that goes to the trigger input on the 555. So I trigger that, and now the output of the 555 is high, and we would expect that to remain high for about 20 seconds because of this RC time constant established by these components. And there we go, it's gone back to low again. So this is basically being a 20-second timer controlled by this transistor. Obviously none of the rest of the circuitry is here at the moment. So I think what I'll do next, because this Q4 is switched output from the 555, so this is meant to drive some LEDs. So I'm going to solder in all of the traffic light LEDs over here so that we can see what the effect is that the 555 switching has on the circuit. So looking at the board here, there's a whole load that are commoned up here. So these three are all connected together, and that's connected to these three, and all round. So all of those are all commoned up, and they all go through this pin here. So there's a missing resistor here that I need to put in. So that's R7, the 100 ohm resistor, and that seems to be the positive side. So I need to make sure all the LEDs are the correct way round. Now, looking at the picture on the website, the green LEDs are the ones on the outside, and then the red LEDs are the ones on the inside. So I need to put them in that orientation. Let me show you where I got to. So I've got some of the LEDs in place now, and so I can show what this does. If I put a positive voltage on the base of this transistor now, you can see I've got some LEDs lighting up. So they're the two reds opposite each other. So this represents the the road junction, so four-way junction. So these two have got a red, and these two have got a green. This one's not lit because I've unfortunately broken a track on the back. So this is the beginning of seeing it working, basically. So we've got no, it's Q4, isn't it? The Q4 transistor is controlling 2 reds and 2 greens. You'll see the kind of problems that I've run into here. So a lot of these tracks are absolutely tiny, and you can easily break the tracks and the pads while assembling it, so it's not really very easy. The other problem I found is that all of the LEDs are meant to share this single resistor, but that doesn't really work, because if you put a red LED and a green LED in parallel with each other, basically the red LED comes on because it's got a lower forward voltage. So let me just explain that. So the way they've set up this circuit is we've got plus 5 volts here, we've got a 100 ohm resistor, and then what they've tried to do is they'll put a red and a green together like this, and then that goes off through the transistor which is switching it. So this is Q4. It's ground there. So basically the idea is you switch on the transistor and the current flows down to ground, right, which should light the 2 red LEDs and the 2 green LEDs. So all the LEDs are in parallel here, I should say. So all 4, 2 reds and 2 greens, are all paralleled together. But the reason this doesn't work is because when you've got a LED with its series resistor, what happens is, so you've got 5 volts here, you've got ground here. What happens is that the LED has a characteristic forward voltage, so when it's properly conducting, you've got, for red it's about 1.6 volts, I think. So you've got a drop of 1.6 volts here, and the remainder of the 5 volts is across the load resistor. So that's red, but for green, the characteristic forward voltage, I measured for one of these rectangular LEDs, and it was something like 2.9 volts. So you need 2.9 volts across the LED before it will light. So if you short circuit a 2.9 volt LED with a 1.6 volt LED, you end up with the red LED on all the time and the green won't come on. So this circuit, certainly with the LEDs that are being supplied in the kit, can't really work properly, and so what I've had to do is basically redesign this circuit so that the red has a 100 ohm resistor and the green also has a 100 ohm resistor. That still goes to plus 5 volts, and that goes to the switch, and that will work because you can have varying amounts of voltage across the current limiting resistor. So I've had to do that, which is why it's so ugly, and I've got the 2 extra resistors on the back of the board, and I imagine that I'm going to have to do the same when I come to connect up the 2 other reds as well. So the next phase, I think, is to populate U1, which has some kind of relationship with U2. So here's a circuit diagram that I've worked out. So you see we've got U1, which is another 555, and we've got the reset is controlled by U2, which we've just built, and also we've got the output of U1 controlling this transistor, which can cause the U2 to reset. So there's obviously a two-way relationship between U1 and U2. This is also an A-stable, so we've got the resistor and capacitor here, so it's running in some kind of square wave output of its own, but it's going to be interesting to see the interaction with the chip that we've already put there. Now the output of U1 also goes through this transistor here, Q2, and this is driving 2 reds and 2 greens. So these are the 2 reds and the 2 greens opposite the ones that we already saw that are controlled by U2. So this is like the opposite phase. And also I've begun to decode this part here, so the 4011 with the NAND gates. So 3 of the NAND gates in that package are used, and it's obviously making some kind of decision based on the outputs of the circuitry that we've already seen, and in turn this goes to U3, which is another 555, and this controls the reset of U3. Incidentally, along the way I also found out that transistor Q5 drives the 4 amber lights, so all the amber lights change in the same sequence. So I guess we'll get to that in the not too distant future, but for now what I'm going to do is I'm going to build U1 and put in all of its support components, and then we'll see what the circuit does then. Okay, so now we've got U1 fitted also, so we've now got 2 phases of the traffic lights, so it'll stay in this configuration for about 20 seconds with the greens in this direction, the reds in that direction, and then there we go, it flips over, so we've got the reds in this direction, the greens in this direction. So basically all of the rest of the circuitry now, the third 555, the 4011 CMOS, and the other drive transistor Q5, that's all for the amber lights now. So it's actually quite a complex circuit for doing quite a simple thing. I'm wondering, you know, how much all of this complexity really needs to be there. Taking a look at the back now, I mean, this is all starting to look like a bit of a nightmare now. So I've had to put the 2 separate load resistors for the green and the red because of that problem with the red effectively short-circuiting the green LEDs. So as this circuit is designed, I don't think it can really work properly. So I hope I've got the amber lights the right way round, otherwise it's going to be a real problem getting the soldering iron in there to flip them round. So the next phase obviously is to put in the CMOS chip here. I think maybe we'll put in the CMOS chip and then get the logic probe on there and see what the result is of the various inputs coming out. So why the output, why there are 3 NAND gates in use on this circuit. So I might do that first before we proceed to putting that final 555 on, which is obviously for driving the amber LEDs. So now I've got the CMOS chip in place, and so this is obviously generating a little pulse to make the amber lights come on. So if I put my logic probe on pin 3, which is the output of the various things going into the CMOS chip, pin 3, so that's the output, so that's showing low at the moment, but look what happens when the light phase changes over. There's just a little sort of maybe 1 second, for 1 second the output of that pin goes high, so this is going to be what triggers the amber light. So probably coming up to the time again, so just watch as the lights change from green to red. There we go, there's just a little flicker as the output of the CMOS goes from low to high, so I'm guessing that these traffic lights are sort of American style traffic lights rather than the British style. So we'll just see a flash of amber, I think, when we've got it all fully assembled. So there we go. So there's just some remaining components to put in now. So we've got the final 555 U3 and a few support components. There's a capacitor over there, and Q5, which is the output transistor that has all of the amber lights connected to it. And here's a quick preview of the schematic for U3, so the final section here. So obviously the output of this 555 is driving transistor Q5, which switches on these 4 amber LEDs all together, and the reset for this 555 is coming in from that pin that we were just looking at, the 4011, what I'm calling gate C, so the bottom left hand corner gate. So again, you can see this is the 555 in its astable configuration. So you've got the resistors and the capacitors, which are setting the clock rate, so the rate of square wave pulses that are generated by the chip. But in this case, the external chip is causing a reset, so will change when the pulses happen out of this component. So anyway, we'll put those components in and we'll see what that looks like. Okay, so the kit's assembled now, but it's working a bit strangely, I think. So going back this way, when it goes from green to red, we get green, amber, red, and that seems okay. But going back the other way at the end of the cycle, it's doing something really weird. So that was okay. You see, it went amber, red, but when it goes back the other way, we get red, amber, green, and then it goes amber, green again. Now I don't know if that's the legitimate pattern of traffic lights in some country or other. I mean, it's not the way that traffic lights work in the UK, and I think if I remember right, in the US, the way that it works is the lights go straight from red to green at the beginning of the cycle, and then going back the other way you get amber and then red. So I'm not sure what pattern these are executing, and whether the kit is working correctly. In general, I think the design is really complicated. I don't really understand still why it needs 3 555s. It seems that 2 of the 555s are connected together in lockstep, with one controlling the reds on this side and the greens on this side, and then the other the opposite, the reds on this side and the greens on this side. And it doesn't seem that you actually need 2 timers doing that, unless it's because the 555 can produce a lot of current on the output. Maybe they needed the two outputs to light this number of LEDs. And the CMOS chip seems to be there entirely to do this, to produce this magical pulse to make the amber lights switch. So see, it's a really complicated design, and I imagine it could be done simpler. So I mean, looking at the actual execution, I'm not happy at all with these tiny thin tracks, because they can be easily damaged, and I've damaged several of the pads trying to get the LEDs in the correct orientation. And also there's the issue, you know, here I've got these bodge resistors, which were actually needed because if you put a green and red LED in parallel, which is what this circuit tries to do, you know, and everything driven through the same current limiting resistor, then what happens is the red comes on, but the green is effectively short-circuited. So I don't think it's a very well designed kit, and I don't like the layout of these tiny tracks, the way it kind of routes everything, you know, around the houses and between pins and so on, when they could have put some wire links in. So I don't think it's a really good kit. It's certainly not a beginner's kit. I can't recommend it for beginners. It seems to take an awful lot of debugging and effort to make this work. If I had to make this again, I think I would just forget about putting the LEDs on the board here at all. I would probably put them on, you know, like risen up from the board, so I could put an individual resistor in the leg between here and the board, or maybe just take all the wires out somewhere else and mount the LEDs somewhere different than on the board. So there you go. I mean, it's not expensive. It's only, you know, $4.35 I think it was on the site at the moment, but there are probably better kits if you want something to keep you busy. Okay, just to finish off that video, so having completely reverse engineered that circuit and built the kit, ICStation.com actually contacted me and they said, by the way, we do have a schematic, and so they sent me the schematic. They've also posted it now on the website, so I'll make a link to the product page down below and you can look at it for yourself. But essentially, you know, we already extracted the important design principles from it. So you got the two 555s here, the U1 and U2. So we've got the north-south reds and the east-west greens, and then here we've got the north-south greens and the east-west reds, and these two 555s have the same time constant, so the same components here, 22 microfarads, and also they're interconnected, so the reset of one is connected to the output of the other and vice versa. So this is basically going to make them completely synchronized and run in synchrony. So that's what's happening there. And down below here we have the ambers, so the 4 ambers are all wired together with another drive transistor. This 555 here has a much shorter cycle. These components will make it run at about 0.5 seconds, so we should get a 0.5 second output high there. And then the other part is the NAND gate, of course the quad NAND gate, of which three of the gates in the package are actually used. So you've got these ones that come from U1 and U3, which basically this will create a short pulse when there's the change from red to green. So you've got these pulses coming out, and then these are combined with a third NAND gate, and if you work out what's happening there, you end up with this kind of waveform. So you've got these short pulses 20 seconds apart. Whenever there's a red-green shift, you get this short pulse, and this short pulse is driving the NE555 here, so that will be resetting this chip. So in principle, what you should get, I mean, this would be like a pulse stretcher, in fact. So you would get a 0.5 second phase of amber whenever the red-green shift happens. So that's what that's trying to do. Why it needs such a complex circuit to stretch a pulse from these, I'm not really sure. I'm sure you could lose half those components at least. And as we saw, it doesn't really seem to work in any case, because you get this strange flickering between the amber and the green phases, and I don't really know why it's doing that, because there's no control from the U3 going back to these other chips, but maybe the power draw is making them trip out or something. I don't know. But there we go, a very complicated and contorted circuit diagram for this traffic light kit. Okay, thanks for watching, and see you next time.